Hello everyone. If you are enrolled in January to April 2026 semester, then you must be watching this video lecture as a part of week 11, as the code IS 1893-2025 has been withdrawn. So, we will be learning the estimation of design seismic load using IS 1893-2016 version. Otherwise, you must be viewing this video lecture as a part of week 2, and so this video lecture may be taken as a substitute for lecture 2.3, which covers equivalent static method for determining design seismic load on a building using IS 1893 part 1 2016. In lectures 2.1 and 2.2, we did look into dynamics of single degree of freedom system, where we learnt about free and forced vibrations. We also looked about dynamic magnification factor and resonance, which is an occurrence when the excitation frequency is equal to the fundamental frequency of the structural system. We also looked into the concept of response spectrum, through which we understood that it is possible to determine base shear and can be utilized to obtain design seismic forces. So, with this understanding of single degree of freedom system and understanding of multi degree of freedom system pertaining to natural period and mode shapes, we shall take our discussion forward to understand how do we estimate design seismic load on a building using equivalent static method. So, any process which is about estimating design seismic load involves 3 steps. The first step would be to estimate the design lateral force on the building. The second would be to distribute the lateral force over the building height, and finally to distribute that lateral force into or among various lateral load resisting members, which are usually columns and shear walls. We use different methods for estimating design seismic load, which are either static in nature or dynamic in nature. In this course, we are looking into equivalent static method and 2 dynamic methods, which are response spectrum and response history methods. So, when it comes to equivalent static method, this is the simplest method for design seismic load calculation and is applicable only for regular buildings with height less than 15 meters in zone 2. So, you cannot apply equivalent static method to determine design seismic load for any building located in seismic zones 3, 4 and 5. We will look about these seismic zones as we go through this lecture. In this equivalent static method, the first step is to determine the total design lateral force for the building. This is based on code estimated fundamental natural period of the building. Our IS code IS 1893 part 1 2016 lists a few expressions for estimating fundamental natural period of a building based on the structural system type. These expressions are very simplified in nature. Then the second step is to determine the vertical distribution of design lateral force across various floors. In this case, the code gives us a very simple formula, which is appropriate only for regular buildings, and this is obviously true as this method is applicable only for regular buildings. After obtaining the design lateral force across various floor levels, then once we have found out the vertical distribution of design lateral force, that is the floor forces, then we distribute those floor forces among various lateral load resisting elements. This is based on floor diaphragm action. So, we will look into these 3 steps one by one. Let us first look into the determination of total design lateral force for the building. For this case, the design base shear for a given building shall be given by AH multiplied by W, where AH is design horizontal seismic coefficient given by this expression Z by 2 multiplied with SA by G divided by R by I, and W is the seismic weight of the building. Now, let us understand various terms involved in AH. We have Z, which is seismic zone factor, which depends upon the location of the site. We have SA by G, which is design acceleration coefficient normalized with peak ground acceleration. We also have R as response reduction factor, and I, which is importance factor. So, we have these terms in the expression for AH, and after multiplying with W, we get the design base shear VB. Now, we also have a minimum design base shear expression provided by IS 1893. So, that minimum design base shear is given as a percent of the seismic weight of the building. It is given in terms of various seismic zones. For zone 2, the minimum design base shear shall be 0.7% of the seismic weight of the building. For zone 3, it shall be 1.1% of the seismic weight of the building. For zones 4 and 5, the minimum design base shear shall be 1.6 and 2.4% of the seismic weight of the building respectively. We will look into detail what we mean by seismic weight of the building. So, let us first look into what is seismic weight of the building. In this case, as we can see, our IS code IS 1893 part 1 2016 through its clause 7.3 gives detail about what shall be the seismic weight of the building, and it says that you have to consider all the dead load, full dead load plus appropriate amount of imposed load while estimating seismic weight of the building. The weight of columns and walls should be appropriately apportioned to the floors above and below, which means that it is about the tributary area. So, usually between two floors, whatever there is a wall or columns, all of them are distributed half to the upper floor and half to the bottom floor. And if you are precisely calculating, then you have to consider the openings appropriately. For example, doors will contribute more to the lower floor and so on. So, it is based upon the tributary area. Similarly, the weight supported in between the stories to be distributed to floors above and below in inverse proportion to its distance from the floor. It means exactly the same, that is the tributary area concept. However, what is the appropriate amount of imposed load that we need to consider in seismic weight of the building? If our imposed load is up to and including 3 kilonewton per square meter, then we need to consider 25% of the imposed load as part of our seismic weight of the building. If it is more than 3 kilonewton per square meter, then in that case we need to consider 50% of the imposed load of the building. So, once we have understanding of seismic weight of the building, now in this expression we have different terms in order to obtain the value of AH. So, let us understand about these terms one by one. So, first of all, we will look into seismic zone factor, which depends upon where are you going to construct the building. So, the country is divided into 4 seismic zones, zones 2, 3, 4 and 5. As we go to the higher zone, the seismicity is higher. It means earthquakes will be frequent, there will be larger magnitude earthquakes and so on. So, as you would be able to guess that some regions in Himalayas as well as the northeastern India have higher seismicity. So, they are assigned zone 5. On the other hand, the peninsular India has lower seismicity, and therefore, you will find that they are assigned a lower seismic zone. Now, this is also based on historical seismic data of various regions, that is based on occurrence of past earthquakes, their damage intensities, etc. So, for different seismic zones we have the seismic zone factor given by this table 3 of IS 1893 part 1 2016, while zone 2 has a seismic zone factor of 0.1, zone 3 have seismic zone factor of 0.16, zones 4 and 5 shall have seismic zone factors of 0.24 and 0.36 respectively. Means for constructing identical building in a place which is located in zone 5, you are roughly increasing your design seismic load by 3.6 times compared to the same identical building being built at a place located in seismic zone 2. So, now we have looked into seismic zone factor, we will now look into importance factor. So, the importance factor in seismic design depends on the importance of building based on its functional utility. It is given in clause 7.2.3 and table 8 of IS 1893 part 1 2016. This table is obtained from table 8 of the code, which gives the importance factors for different types of building based on their functional utility. So, for a typical building the importance factor shall be 1, but if you have a residential or commercial building where you have the occupancy of more than 200 persons, then in that case the building attracts an importance factor of 1.2. For all other important buildings such as hospitals or school buildings or monument buildings or any lifeline and emergency building which you need after the earthquake, for example hospital buildings or a radio station building and so on, or a bridge in that case where you want the connectivity to remain intact, in that case the importance factor shall be equal to 1.5. Now, we will look into next factor, which is response reduction factor. As we have understood in our week 1 lectures that we can design the same structure for design elastic force or design inelastic force. That is, we can assume that the structure behaves elastically or inelastically, but in either case the design load is very different. How much difference is there? The difference is given by the response reaction factor, which means if you are trying to design a building assuming inelastic action in the building, then your design load will be a fraction of the design load if the building was being designed for elastic behavior, and that fraction is given by response reaction factor. So, response reaction factor is the ratio of design seismic load if the behavior was elastic to the design seismic load if the behavior is inelastic. So, it depends on the type of structure and its lateral load resisting elements. For example, when you have a moment frame, what is a moment frame? A moment frame is a frame where one member transmits the force to another member through moment action, which means the joints are rigid, they are able to transfer moment from beams to columns and so on. So, in that case, if you have reinforced concrete or steel building which have moment resisting frame, they will have R value of 3.0 and 5.0 depending on whether the moment frame is OMRF or SMRF. OMRF is ordinary moment resisting frame and SMRF is a special moment resisting frame. If your moment frame satisfies design conditions or guidelines mentioned in IS 456 for RC buildings and IS 800 for steel buildings, that moment frame will be classified as OMRF. However, in addition to IS 456 for RC building and IS 800 for steel building, if your design also follows ductile detailing guidelines given in IS 13920 for reinforced concrete building and IS 18168 for a steel building, then in that case we call such moment frames to be SMRF or a special moment resisting frame. So, Summarizing, OMRF is designed for safety only, while SMRF is designed for safety as well as for ductile detailing. We will understand more about ductile detailing as we go through this course. Typically, ductile detailing represents that we establish a hierarchy of collapse. In case of braced frame, we will have buildings with ordinary concentrically braced frames or buildings with a special concentrically braced frame. These will attract response reaction factor of 4 and 4.5. Now, at this point I would like to tell that these braced frames usually have higher stiffness compared to moment resisting frame and therefore have limited displacement in the lateral direction, which means they can have a higher value of response reaction factor. And again, the difference between OCBF and SCBF is very similar, that if you follow the ductile detailing provisions, then in that case it will be called special concentrically braced frame. If you do not follow the ductile detailing provisions, then your frame shall be OCBF. Then you have buildings with special eccentrically braced frames, commonly called as EBF. The response reaction factor shall be equal to 5. Now, these CBF and EBF are lateral load resisting systems typically found in steel buildings. Okay, for eccentrically braced frame, you will be knowing or you will come to know that these EBFs have shear links in them, which act as a structural fuse even before the braces get damaged. So, depending on the hierarchy of collapse established or how many layers of failure can be allowed, depending on these you will have response reaction factor also. So, the higher response reaction factor means you have higher redundancy in your structure. Now, if we look into various structural wall system, then in that case, depending on whether the wall is made up of unreinforced masonry or reinforced masonry or a confined masonry or reinforced concrete shear wall, whether it is ordinary or ductile, depending on whether it satisfies the ductile detailing provisions given in IS 13920 or not. Depending on all of these, you have different values of response reaction factor known to you from IS 1893. Now, all of these are contained in table 9 of IS 1893 part 1 2016. I hope that you have a copy of IS 1893 part 1 2016. This code contains information about determination of design seismic load for general case as well as buildings. Now, once we have understood response reaction factor for different buildings, reinforced concrete, steel and masonry, let us also look into some other buildings which can have dual systems, where you can also use RC structural wall in addition to RC, OMRF or SMRF, etc. So, for these also the code specifies the values of response reaction factors. Once you have the understanding of response reaction factor, now let us look into the design acceleration coefficient, which is SA by G. Now, SA by G or the design acceleration coefficient depends on natural period of the building, damping in the building and underlying soil type. We have these three factors that affect SA by G. The value of SA by G is given by these expressions which have been obtained from the relevant clause of IS 1893 part 1 2016. The same is given over here in form of plot. This is also obtained from IS 1893 part 1. So, you can have a look in the code as well. Now, at this point you can notice that on the x axis we have the natural period of the building, on y axis we have SA by G. So, with variation in natural period of the building, the value of SA by G also changes. It reduces after a certain limit, and then for variation in damping ratio you will have difference in these curves, you will have a different curve altogether. So those curves are not given in the code because it has been assumed that these curves pertain to damping ratio of 5%. So if you have damping ratio which is different than that, then we have to use some multiplying factor. We are not looking into much detail about those multiplying factors in this course. So another thing which you can notice in this plot, that there are 3 different plots, and these are for different soil types, whether the underlying soil is a rock or hard stratum, whether it is a medium soil or a soft soil. Now for building on soft soil, now for a building on soft soil, the value of SA by G will be usually larger than an identical building founded on rocky or hard stratum. Okay. So once we have understood these factors, now we can calculate what will be the design base shear or the design seismic load. How will you calculate? You will first calculate the value of AH, which is given by Z by 2 multiplied by SA by G divided by R upon I, and then you will multiply that AH with seismic weight of the building W to obtain the design seismic load. That shall be the design base shear as well. Once you have the design, but in this case you also observe that we will need the natural period of the building. Now in order to obtain the natural period of the building, code gives simplified expressions. The simplified expressions are given over here. These have been adapted from code, particularly clause 7.6.2. For example, for reinforced concrete moment resisting frame building, we have a natural period which is given by this expression. For RC steel composite MRF building, that is moment resisting frame building, you will have the natural period given by this expression. Now this is somewhere in between the expression given for RC MRF and steel MRF. Now for all other buildings, including buildings with shear wall, you will have other expressions given over here. For example, buildings with RC shear wall have natural period given by this very expression, and it can not be lower than this very value, which is usually used for finding natural period for all other buildings. We also understood that SA by G depends on different site conditions, whether your underlying soil is rocky or hard stratum, or a medium soil or a soft soil. So this classification is based on various soil properties, the gradation of soil, the composition of soil, whether it is gravel or sand or clay, and sometimes even SPT value is also used to determine what is the soil type at that location. Therefore, it is necessary to conduct a thorough geotechnical investigation of any site before we get into structural design for the building. Now this is obtained from table 4 of IS 1893 part 1 2016. You can have a look into the table of the code so that you get more familiar or understanding on the issue. Now once we have all the factors known to us, then we can obtain the design base shear, which shall be obtained as H times of W. AH shall be given by Z by 2 times of SA by G divided by R upon I. After finding the design base shear, it is time to find out what shall be the forces, lateral forces being applied on various floor levels. How shall we find that? Or in other simpler words, we need to distribute the design base shear at different floor levels. So for that we have an expression given over here as design lateral force at floor I given by WH square divided by sum of WH square for all stories, and then we have to multiply with the design seismic force or the design base shear which we have obtained. Now Wi is the seismic weight of the floor I, Hi is the height of the floor I measured from base. What is the base? it is the base of the building. For a precise understanding, I suggest that you also look into the code IS 1893 part 1 2016, where it will define what is the base. Okay, n is the number of stories in the building, that is number of levels with lumped mass. Now, after finding the design lateral force at different floor levels, you can cumulatively add from top to find the story shear for any given story. For example, in case of a 3-story building, the story shear in the ground story shall be equal to the sum of all the lateral forces being applied at different floor levels above the story. So, that is why it is written Vj shall be equal to sum of Qi, where I ranges from j to n. So, it is the sum of all those lateral forces. Now, once we have the story shear known to us, we need to distribute that story shear among various lateral load resisting systems, which are usually columns and shear walls. So, how do you distribute that? If your slab is able to provide you a rigid diaphragm action, then that story shear force is distributed in proportion to stiffness of various lateral load resisting elements, which means a stiffer column will attract a larger chunk of the shear force in the story. If your slab is not able to provide you rigid diaphragm, at the same time, if your slab is not able to provide you rigid diaphragm action, that is the diaphragm action is flexible, then in that case it is distributed considering flexibility of the diaphragm. IS 1893 part 1 2016 is silent about how do you calculate the flexibility of the diaphragm, or in what proportion then you distribute the design shear force and so on. But the point to mention over here is that the further revision of the code may involve the distribution in case of flexible diaphragm action as well. Some codes around the world suggest it to be distributed in proportion to the tributary area if your diaphragm is flexible. Now, how will you know whether your diaphragm is rigid or flexible? So, if the maximum lateral displacement measured from the chord of the deformed shape at any point of the diaphragm is more than 1.2 times the average displacement of the entire diaphragm, then in that case we can tell that the diaphragm is not able to stiffly hold all the lateral load resisting system, and therefore the diaphragm is actually flexible in nature. The general thumb rule for rigid diaphragm action says that all the reinforced concrete monolithic slab beam construction, which is the typical case for in situ construction, in that case the rigid diaphragm action can be assumed. In case of precast elements, we have some details related to how much screed concrete or how much is the minimum reinforcement and maximum aspect ratio. All these details will give you an idea about whether the slab is able to provide the rigid diaphragm action or not. So, having understood the estimation of design seismic load, the vertical distribution of design lateral forces, and then in plane distribution of story shear forces, we have now come to the end of this lecture. In the next class, we will see an illustrative example which will take you through all these steps in order to find out the design seismic load based on equivalent static method. Thank you.